All right, I think it's about time that we can get started. I have the pleasure of introducing Dr. Amat Tafti. Amat is from Iran, where he received his bachelor's and also master's degree in computer science, specifically software development. He also has a strong background, some of the Berk people will know about this, as an enterprise Oracle DBA. He studied image processing, medical image analysis, visualization, and retrieval at Technical University in Vienna and Medical University of Vienna in Australia. He's also done coursework in practical machine learning and R programming at Johns Hopkins. And last year, he received his PhD from the University of Wisconsin-Milwaukee in computer science, where he focused on computational methods, including machine learning, computer vision, and optimization algorithms. He's really a smart guy. Dr. Tafti came to Marshfield Clinic Research Foundation as a research intern in the Center for Human Genetics, and more recently he came to the Biomedical Informatics Research Center as a postdoctoral scholar. So I'm excited to present Dr. Tafti, and today he will be presenting parts of his thesis regarding 3D surface modeling. Welcome.
Thank you, Peggy. Hello, everybody, and thank you for coming to the talk. My name is Amat Tafti, and I am coming to you from Biomedical Informatics Research Center at Marshfield Clinic Research Foundation. Today, I am going to talk about 3D surface modeling of microscopic objects, a computer vision adventure. Here is the brief outline of the talk. I will first give you a brief introduction to computer vision. Then I will jump into 3D surface modeling of microscopic objects by defining the problem statement, methods, and I will finish with experimental results, conclusion, and outlook. What is computer vision and why should bother this? Computer vision, as a very fascinating computational method, deals with how computers can see and understand from digital images and video sequences. Many computer vision algorithms are available now, which aside from lending practical and theoretical contributions to other fields, have demonstrated successful applications in image segmentation, object recognition, and 3D surface modeling, which is the major part of this talk. Let's talk about our problem statement. Scanning electron microscope as an advanced imaging equipment has been widely used in many scientific disciplines, including biological, mechanical, and material sciences, to determine the surface attributes of microscopic objects. While SEM images still remain two-dimensional, many research and educational questions truly require facts and information about their 3D surface models. 3D surface modeling of microscopic objects would provide true anatomic shape, offering informative visualization for a system being investigated. What does 3D SEM surface reconstruction mean, or what we mean by 3D SEM surface reconstruction? When you take a photo from a real microscopic sample, you actually convert all 3D points on that scene into 2D points in an image plane. By 3D SEM surface reconstruction, we tackle the inverse problem, going from 2D to 3D. For better clarifying the purpose of 3D SEM surface reconstruction, we put an example here. At the left side, you can see a set of two-dimensional images from a biological sample called typical cell. On the right side, you can see the 3D surface reconstructed model using our proposed method. So the problem here is going from 2D to 3D. All 3D SEM surface reconstruction algorithms in the literature are divided into three major classes. The first class called single view, in which a set of two-dimensional images from single perspective by varying light directions are considered for 3D surface modeling. The second class is multi-view, in which a set of two-dimensional images from different perspectives are considered for 3D surface reconstruction. And the third class called hybrid, that tries to combine single view and multi-view together to tackle the problem of 3D surface reconstruction. In this table, we summarize the advantages of and also disadvantages of these algorithms. While single view approach can be easily implemented at an appropriate computational cost, the 3D model would be limited to only a particular viewpoint. Multi-view algorithm can produce and provide and generate better 3D model, but they need more sophisticated algorithm and computational time. Hybrid algorithm can take advantages of both single view and multi-view approaches, but they are not operational and appropriate with common SEM machine. So based on their cons and pros, we selected multi-view approach in this study. The motivation of the work is to revisit the state of the art of 3D SEM surface reconstruction to provide better understanding of the work and bring advanced 3D technology into scanning electron microscope community to create realistic anatomic shape from microscopic samples, to allow rotation and depth for further interpretation of microscopic objects, and to provide informative visualization for a variety of applications in biological, material, and mechanical sciences. The objective of the work is to design and develop an optimized, intelligent, and adaptive framework to tackle the problem of 3D SEM surface reconstruction. In doing so, we wish to account for a set of two-dimensional SEM micrographs that take from different perspectives, multi-view geometry, optimization strategies, and machine learning algorithms. In the following slides, I am going to talk about our proposed method. Before that, I want to show you a taxonomy of 3D SEM surface reconstruction algorithms. All green boxes you see here, they are implemented and developed by previous work in the literature. Our work would be the first to develop optimized multi-view approach for 3D SEM surface reconstruction. In addition to that, we improve the accuracy, reliability, and efficiency of the method by adding two quality attributes, including adaptive and intelligent strategies. Here is the pipeline of the work. So as you see, pipeline begins with taking several 2D images from SEM from a scanning electron microscope. Once we have done with this step, we need to detect and describe feature points in every single image. Then we need to find matching points or corresponding points in the image set. Once we have the matching points in the image set, we can utilize epipolar geometry or multi-view geometry to estimate rotation and translation, the rigid body transformation from the first image to the second image in the set. And then we can utilize linear triangulation to estimate and initialize the 3D location of all matching points in the images. The last step is optimization process, in which we try to find the best fitness model for a set of parameters, including rotation, translation, and also the 3D locations. So the first step, we need to take several 2D images from scanning electron microscope. Scanning electron microscope Scanning electron microscope offers excellent capabilities to overcome the limitation of human eyes by achieving increased magnification, contrast, and resolution greater than 1 nanometer. There are 5 major components in a SEM including electron gun, scanning system, lens control, detectors, and display system. Electron beam emitted from the electron gun can induce different signals, including secondary electron and backscatter electron, yielding different types of digital images. While SE detector can produce and can generate higher resolution and darker intensities, BSE, I mean backscatter electron detector, can produce lower resolution with brighter intensity. Based on our study and like previous experience, we use SE detector in this study because SE detector is able to provide high resolution images, which is more appropriate for 3D surface reconstruction. Okay, in step 1, we just take several 2D images from different perspectives of a microscopic sample. Then, as I said, we need to detect feature points in every single image. But by feature point, I mean something like edges, like corners in every single image. There are some algorithms such as SIFT, SURF, ORB, and GRIF that help us to detect feature points in every image. We actually applied all of them, but based on their efficiency, accuracy, and the number of feature points they can provide to us, we pick SIFT algorithm based on our experience. Once we found feature points in every single image, we need to find out and discover matching points in the image set. KNN, which stands for K nearest neighbor, and RANSAC, which stands for random sample consensus, help us to tackle this problem. Let's further discuss about matching points and how we can find matching points in the image set. Let's say we have a 3D point A here, and we can observe 3D point A from two different views. We call the projection of A in image, let's say for example image 1, xi, and the projection of A in the second image, we call it yj. In that case, there is a projective transformation like h such that yj would be equal to hxi. So the problem of discovering matching points is to explore a subset P of 1 to n, which is the number of feature points in image 1, times 1 to m, which is the number of points in image 2, and also a homography transformation h such that two following rules meet. The first rule is saying that the distance between two corresponding points or two matching points should be less than a threshold sigma d, meaning that two matching points or two feature points are similar to each other. The second rule is saying that the distance between two feature points should be less than another threshold called sigma g, meaning that homography transformation constraint is satisfied. So, in the previous literature, computer vision researchers only utilized fixed threshold for sigma d and sigma g. In this work, we utilized a statistical method called contrario strategy to dynamically set value for sigma d and sigma g based on our SEM images. In this slide, you can see the results obtained by contrario strategy. Like in this example, you see the number of matching points found between two images without using contrario strategy is about 2,000 feature points, true matching points, matching points. And in same images, we got almost 3,000 number of true matching points using contrario or adaptive strategy. Feature matchings need comparing a large number of multi-dimensional descriptor vectors. We apply a machine learning technique in which a binary classifier to distinguish significant versus insignificant feature points in images will identify feature points that are useful for the matching process. These attributes speed up and increase the accuracy of finding and discovering the matching points in the image set. To make a classification function, as you know better than me, a training data set is needed. We made a training data set by utilizing a collection of 8 groups from different SEM images, including almost 167,000 feature points. Each group consists of several SEM micrographs that are visually similar to each other, and they are captured by tilting the sample stage by different angles. A feature point is labeled significant, where there is a correspondence in the image set. Otherwise, we call it insignificant. So the problem of machine learning here is kind of binary classification. So in this slide, I'm going to talk a little more about multi-view geometry. In homogeneous coordinate, a 3D point X is described by the vector X, Y, Z, and 1, where X, Y, Z are its position in Euclidean space. The projection 2D or 2D projection of X on the image plane we call X would be U, V, and 1 is computed as this equation. X would be P times capital X, this 3D point. This is the projection matrix of the camera or projection matrix of the SEM machine, and this is X in the image plane. This is 2D. So the projection matrix of the camera would be A times ID times the size of 3 and 3, and rotation and translation. A is the internal parameter of the camera. So the idea is that we have a 3D scene here, and we have a set of 3D points here that we can observe from different views. For now, suppose that we just have 2 different views, and we can see X in 2 different views. What we know here is the internal parameter of the camera, including focal length and the principle of the camera. What we don't know is rotation and translation, the rigid body transformation from the first camera position to the next one. So, as you see, the problem has 2 sides. We need to estimate rotation and translation between images, and we also need to initialize the 3D location of all matching points. And believe me, this is nasty chicken and egg problem. What I mean by chicken and egg problem is that once you have rotation translation from the first image to the next one, you actually have the 3D point. And when you have a 3D point, it's actually rotation and translation between the images. Using essential matrix and fundamental matrix, we can easily compute rotation and translation by only having 8 number of matching points between images. Once we know the rotation and translation between the images, we can estimate the projection matrix. Let's say we have projection matrix. So we know that from the previous slide, we know that X in 2-dimensional would be projection matrix times capital X in 3D. So we can say that X would be equal to, we expand the matrix like this to the 3D location, X, Y, Z, and 1. So as you remember, in 2D, we can call that U, V, and 1, and this is the weighting score. This is the projection matrix times by X, Y, Z, and 1. So we will have these equations, W, U, P1X, which is the first row of the matrix, W, V, P2X, the second row, and also W, P3X. So we can convert these guys to this one. And having such equation, we can utilize least square method to find the value of x, y, z. So we can get the location of the 3D point. Using the general pipeline of 3D SEM surface reconstruction, we normally initiate the 3D points and also rotation and translation with some error threshold. Suppose that we are given two-dimensional images with n number of matching points. So the problem here, or like the minimization function here, would be such a guy in which x1 to xn they are 3D points. R and T would be rotation and translation. X is a 2D projection matrix in the first position of the camera, in the second position of the camera. So as you see here, in this equation, parameterization, the space of rotation and translation is the major part of the work. So to have the better flexibility of the work, we utilize quaternion parameterization to estimate the 3D rotation and to optimize this equation. A quaternion Z would be equal to A plus BI plus CJ plus DK, where A, B, C, and D are real numbers, and I squared equal to J squared equal to K squared equal to -1. And Z is the unit quaternion if only if absolute value of Z equals to square root A squared plus B squared plus C squared plus D squared would be equal to 2. And the rotation representation or matrix of the rotation using quaternion approach would be something like this. We also need, beside rotation estimation, we also need to estimate translation over the x-axis, over the y-axis, and over the z-axis. So our problem will be finding a vector including A, B, C, D, 4 parameters for rotation and 3 parameters for translation. So the optimization problem would be something like this. In previous literature, computer vision researchers usually employ local optimization in which it needs some initial guess relatively close to the answer to find the best fitness model, but in this work we utilize differential evolutionary approach that is kind of global optimization strategy. In the following slide, I will talk about experimental validations. First of all, I want to discuss about the data set we have. As you see, we utilize 4 different data sets, including typical cell, diatom frost tool, artificial dental erosion sample, and TEM Cocker grid with different angles, tilting angles, and also different number of 2-dimensional images and different image attributes. All part of the framework designed and developed by Java Standard Edition 8, and we also employed MATLAB in some part of the work, We did all experiment using 64-bit Windows operating system, Windows 8 operating system, and also we utilized a personal computer with i5 3 GHz Intel Dual Core, 4 MB cache, and 6 MB RAM. In this slide, you see qualitative 3D visualization for a biological sample called typical cell. In the first row, you see a set of 2-dimensional images, and in the bottom, you see the 3D surface reconstructed model using our framework. The set of 2-dimensional images were obtained by tilting the sample stage 9 degrees from one to the next in the image sequence. In the next slide, you see the same results for diatom first tool. The 2D images were obtained by tilting the specimen stage 15 degrees from one to other in the image sequence. And in this example, you will see qualitative 3D visualization for artificial dental erosion sample and 2D images, the sample stage tilting by 2 degrees from one to the next in the image sequence. And as you see here, in this example, we also capture the texture of the images in the 3D model. In the 3D model, you can also see the texture of the images. And in the last example, you will see qualitative 3D visualization results for a material object called TEM copper grid. Here in this slide, you will see the accuracy results in SEM calibration. As you remember, our problem had two sides. One estimating the 3D location, and the other one is estimating rotation and translation between images. We called it SEM calibration. At the first column, you see a set of different 2D images, 2D SEM images. And the second column, you see the total number of matching points, the rotation angle given by a SEM machine, and the number of generation for differential evaluation algorithm, which we utilize as an optimization strategy. And delta R is the difference between the rotation angle given by SEM and the rotation angle we estimated. And as you see, the delta R varies from 4.9 to 4.98 E minus 4 to 5.80 E minus 3 in this example, which is really promising, relatively close to 0. In this experiment, we compare our 3D SEM surface reconstruction framework with two other traditional approaches in the literature. ADBA stands for Algebraic Distance Bundle Adjustment, and ASDBA stands for Adaptive Simpson Distance Bundle Adjustment. And as you see in this experiment, our proposed framework were able to generate more promising results rather than two other approaches in the literature. Let's talk about the performance of the classification algorithm. There are three common ways to evaluate a classifier called accuracy, precision, and recall. Accuracy is what % of the prediction are correct. Precision is what % of positive prediction are correct. And recall is what % of positive cases are detected. As you see in this experiment using support vector machine, we got over 93% in accuracy, over 94% in precision, and over 91% for recall. So based on this experiment, we utilize support vector machine to distinguish between significant and insignificant feature points that help us to speed up the process of finding and discovering matching points in the image set. Here you can see the convergence rate of the optimization strategy we utilized. So as you see, it tends to 0, and after a certain number of generation, it remains stable. How we can validate this 3D surface model from microscopic samples? There are different 3D face models available on the internet, mostly provided by universities across the country, like Stanford and MIT. They utilize laser scanner to obtain 3D surface model of the face. We got those models and utilize MeshLab, which is a mesh processing software, to take 2D images from those 3D models. Having a set of two-dimensional images, we apply our algorithm to find out the 3D surface model of the face, and then compare our 3D surface reconstructed model with the reference model provided by that university. So, and then utilize Hausdorff distance to measure how they are similar to each other. Hausdorff distance tells us how much two metric spaces are similar to each other. And as you see in this experiment, it's again promising. Like the minimum value of Hausdorff distance between two different models, one model obtained by our algorithm and one model obtained by laser scanner, relatively close to each other. There is some sort of limitations. I mean, our algorithm would not work in some sort of SEM images. This is a few, these are just few examples. The first one, when we have some like dark area including shadows, the algorithm are not able to detect feature points, and also it is not able to find out and explore the 3D surface model of the objects. The other limitation is that when we have a complex surfaces, we are not able, using this algorithm, we are not able to find out the accurate 3D model of the microscopic object. So in this slide, I'm going to summarize the experimental validations. As you see, experimental validation showed us SEM images are appropriate for 3D SEM surface reconstruction. Comparing two other traditional methods, our proposed method has provided better 3D results and also provide better results in SEM calibration. Number of correct matching points has a crucial impact on the quality of 3D surface model. Not all of images, as you see in the previous slide, are not appropriate for 3D reconstruction, like flat surfaces, very complex surfaces, and also dark and shadowed surfaces are not appropriate for 3D surface reconstruction using such algorithm. In conclusion, we can say using a variety of computational methods, we designed and developed an optimized adaptive and intelligent strategy and framework for 3D SEM surface reconstruction. To the best of our knowledge, our work is the first attempt to tackle the optimized multi-view approach for 3D SEM surface reconstruction. The main problem is that both single view and multi-view 3D SEM surface reconstruction are applicable for only those surfaces that are visible in the images. The other problem is that we may have to reconstruct 3D surface model from a small number of SEM images because we have a limitation in tilting angles in SEM. The tilting angle in a SEM machine would be limited from 0 to at most 75 degrees. But in reality, we don't have such a limitation. The outlook for future work, we actually like to utilize low level and also medium level image processing techniques to something like shadow removal. In that way, we can also recover the 3D surface model from like dark surfaces. We also need to focus and concentrate on application area. We already generated a reliable and robust framework, but we still need to think about application area. We also need to work on dense matching instead of sparse matching, and dense reconstruction instead of sparse reconstruction. And we really like to plug 3D SEM, our 3D SEM framework into plug and make it available for the research community across the world. These are our achievements. We are the first to design and develop and optimize intelligent and adaptive strategy multi-view 3D SEM reconstruction approach. We are the first to study a taxonomy of 3D SEM surface reconstruction. We are the first to provide SEM surface reconstruction dataset, which is publicly and freely available to the research community. In this address, you can go to http://celibcv.org 3D SEM to see 2D images and also 3D surface reconstructed models. We are the first to investigate and initiate the application of 3D SEM surface reconstruction, particularly in tribological analysis of microscale surfaces. Using such framework, we are able to measure flatness, waviness, and roughness of 3D surface models or 3D surfaces. I mean, we are not just able to see the 3D visualization. We are also able to measure the roughness of the surfaces and waviness and flatness of the surfaces, which would be more appropriate for some further studies and interpretation of microscopic objects. We also initiate the study of SaaS-based, software as a service-based architecture and web services for 3D SEM surface reconstruction studies. These are our publications in this field, including conference and journal publications. We were fortunate to receive GE Healthcare Honorable Mention Award as part of this work in 2015. Our framework called celibcv and the database called 3D SEM has been announced with Computer Vision Online, which is a very well-known community in computer vision area. And we were fortunate enough that Harvard dataset has been also announced our dataset, so you can also go to the Harvard Dataverse and take advantages of our dataset, which is publicly available to the research community. If utilizing Google Scholar, if you search 3D SEM surface reconstruction using different terms, using different words, like 3D SEM advances in 3D SEM or 3D SEM surface reconstruction, something like that, our work would be at the first page of the Google Scholar, which is really promising, at least to us. I would like to acknowledge many people without whom this work was not possible. I would like to thank Dr. Yu, Dr. Munson, Dr. Suzuki, Dr. Owen, and Dr. Baghaie from Milwaukee, University of Wisconsin-Milwaukee, that helped us much to tackle the problem of 3D SEM surface reconstruction. In addition to them, I have many friends here, there are just few, believe me, that I would like to thank all of them for their always kind consideration.